Here we have this integral from 0 to pi of x over 1 plus cosine square x dx. And to solve for this integral, we will first prove this lemma and this lemma. Because the difficulty of this type of integral is that it's not easy to find antiderivative. Just by first glimpse, it's not immediately obvious. But using these lemmas, we may be able to somehow turn this integral into some simplified integral where we can easily find out the antiderivative. Now, to prove this identity, I'm going to let x equal to a plus b minus t. So therefore, t is equal to a plus b minus x. Therefore, dx is easily just minus dt. So again, we have to also change the boundaries. So remember, when x is equal to a, t is equal to b. Likewise, when x is equal to b, t is equal to a. So therefore, I can now turn my original integral from a to b of f of x dx into integral from b to a f of a plus b minus t. Then dt, we have a minus sign out here. Now, therefore, I can simply switch the boundaries and get rid of the minus sign. So from a to b of f of, now I'm going to change the t's into x's. Now f of a plus b minus x dx. As long as we have consistent variable, then we're safe. It's perfectly legal. Now, so that proves this identity. So graphically, if we draw now, for example, this is the graph of the original function. And we're integrating from point A to point B. So that is this area. Now, it's easily verifiable that our new function is in fact symmetrical to the original function according to this line. This line that passes the middle point of A and B. Now, in other words, our new function will look like this. Now, just from the graph, it's obviously clear that our original integral is equal to the new integral exactly, right? Now, the second identity, this, right? So our original integral can be written into this. So the reason is because it's also easy to verify that f of x plus f of a plus b minus x, this function as a whole is in fact symmetrical also according to this line. Now, if we want to integrate it, right? If we want to integrate it from a to b dx, then that is essentially equal to integral from f plus, we can just split it into two integrals, f a plus b minus x. Now, since we've proven that this integral and this integral are equal to each other, therefore that is just twice of integral from a to b of f of x dx. And since since it's easily verifiable that this integrand is in fact symmetrical to this line, therefore we can just simply work out the integral from a to the middle point and then double it. Right? So double the integral from a to the middle point. From the graph, it's easily verifiable. For example, the graph of this whole function maybe look something like that, right? So this graph is in fact symmetrical to this line. Therefore, the integral from a to b is easily just a to the middle point, double it. That is the f of x plus f of a plus b minus x dx. And we just cancel out the 2's. So that is easily this result. So this is in fact a generalized case of the special case where a function is symmetrical according to the origin. In that case, an odd function. Then if we integrate from minus a to a, then it's easily 0. If a function is symmetrical according to the y-axis, then if we integrate from minus a to a, then we can easily just integrate from 0 to a and double that value. But this is just a generalized case where the function is actually symmetrical according to this line. Now, so using this fact, we're going to find out, first of all, what is f of, so first of all, 0 to pi. A is 0, b is pi. Again, using this equation, so from a to half of a plus b, that is from 0 to half pi. And f of x plus f of a plus b minus x. So what is f of x? That is x over 1 plus cosine square x. And plus, what is a plus b minus x? That is pi minus x. Now, x becomes pi minus x. And 1 plus cosine square x. Still cosine square x. The reason is because when we replace x with pi minus x, so that is cosine pi minus x. Because cosine is an even function, therefore this is equal to cosine x minus pi. And cosine x minus pi, that is minus cosine x. And because we just square it, therefore still positive. Now, I just need to work out this integral. Now, this can be easily simplified down to, because x and x just cancel out. And we have a pi on top. Therefore, I just extract the pi. And 0 to half pi dx. And we have 1 plus cosine square x. Now, then I'm going to divide both the top and bottom by cosine square. Now, after I divide everything by cosine square, I have pi times 0 to half pi. And on the top, I have 1 over cosine square x dx. The bottom, I have 1 over cosine square x plus 1. Now, 1 over cosine square, that is the derivative of tangent. Right? So therefore, I'm going to let t equal tangent x. Right? Then dt is 1 over cosine square x dx. That's the motivation. Now, I can further simplify, rewrite 1 over cosine square x into sine square x plus cosine square x over cosine square x. That is equal to 1 plus tangent square x. That is, tangent is t. That is 1 plus t squared. Now my integral just easily becomes just pi times, first of all, since I divide by cosine x, therefore cosine x cannot be 0, and x cannot be half pi, but it can approach half pi. Right? So when x is equal to 0, t is equal to 0. When x approaches half pi, t approaches positive infinity. And on the top I have dt. And on the bottom I have 1 plus t squared plus 1, 2 plus t squared. And I can further rewrite my integral. Can first take out the 2. That is pi over 2. Integral from 0 to positive infinity. There I have just 1 plus t squared over 2. That is t over square root of 2, quantity squared. Now, plus t over square root of 2, quantity squared. Now, that is equal to, remember, we treat t over square root of 2 as a whole entity, therefore it's arctangent. Now, that is a half pi arctangent t over square root of 2. Then we have to multiply by some constant, because if we want to differentiate this expression, then we're going to use chain rule. Then we're going to have to multiply by some constant, that is the 1 over square root of 2. Therefore, I still have to multiply by square root of 2. Right, just to cancel it out. And from 0 to positive infinity. And when t is equal to, when t approaches positive infinity, that arctangent approaches half pi. Right, that is half pi. When t is equal to 0, this is equal to 0. Therefore, my final result is actually square root of 2 pi over 2 times half pi. That is pi squared over just 2 square root of 2.